So the first talk of this second session is by Atindra from SNBNCBS National Center for Basic Science, and he's going to talk about these 2D and raw materials. Please, Atindra.
Yeah, hello and welcome to my talk. So I thank the organizer, especially Chandni, Arindam and Srimanta for inviting me to this very interesting workshop. I'm unfortunate that I could not attend the first part of this meeting, but the good thing is that the talks are available online, so I can listen to that. Okay, so today's agenda is that I will show you some our results on Quasi-2D van der Waals ferromagnet, like some unusual transport behavior and the electron spin resonance experiment, what we have done in collaboration with IISc Dresden. So let me thank the collaborators first. So this was possible because of these PhD students Riju and my postdoc Dr. Buddhadev Pal. So both of them initially started this project, and Riju is continuing this in his PhD thesis. So and the collaborators, like the sample was grown by Professor Prabhat Mandal, who was a faculty at SINP, but now he is an emeritus professor at our center. And theory collaboration by Tanmay Das, and this was a collaboration with Van Bushner and Alexei Alphonsov and Vladislav Kataev, the ESR group. So with IISc Dresden. So, and the funding agency, of course, DST Nanomission and SNBNCBS Center. And we also have a IISc MOU between SNBNCBS Center and IISc Dresden, through which we could send the student and he could do the ESR experiment. So I am from like SNBNCBS National Center for Basic Science. As our director yesterday, Professor Tanushree Sahadas-Gupta mentioned, that we are celebrating the Bose statistics, 100th year of the Bose statistics, and we already have several programs. Out of the 3 conferences are being organized, 2 of them already held, and the last one will be in November, and all of you are welcome to visit our center. So in my lab, I want to give a brief description about my lab, what we do. So we look at the electron transport in nanoscale material to different 3D materials, like to 2D materials. So one of the major direction is, of course, studying the single atomic contact, transport through atomic contact or molecular contact using break junction technique that we have developed in India after I joined SNBNCBS Center. And then we are also working on several charge density of materials, like different quantum materials, looking at the chiral charge density of material, like planar Hall effect, different transport behavior, like you observe unusual planar Hall effect, like change of sign in this material. Then we are also looking at quasi one-dimensional CDW material, where we also observe superconductivity and some weak ferromagnetism in this material. And recently we are working on 1T-TS2, where we are observing some kind of nonlinear Hall effect. Okay, so of course, and we have a large 2D activity, like engineering 2D materials, like we have worked on light matter interaction, optoelectronics in large area 2D 0D hybrid material system. Then recently we have started working on P-type 2D materials, like contact engineering, understanding the defects, noise in this system, like P-type tellurine, then N-type RES2, and also this very recent phenomena is working in the direction engineering 2D organic hybrid material, like 2D, we are putting organic semiconductor on 2D materials like MOS2, and we are seeing some interesting interlayer exciton or similar observation. Okay, but today's talk will be focused on unusual magnetotransport, magnetism and transport behavior in F4GT system. I'll give a brief description about this FGT system to the audience and the ESR measurement in F4GT. So I think yesterday Professor Satyajit Banerjee gave a very nice introduction about this 2D ferromagnet, and he talked about the CGT system, CR chromium based germanium telluride system. And first thing is that till 2016, like almost all the properties in 2D materials have been were discovered, but the missing element was 2D magnets. Okay, and that was obviously because of the Marvin-Wagrove theorem that tells that thermal fluctuation destroy long-range order in the 2D limit. Okay, and however, in 2017, the CRI3 and CGT system came, like in this Nature paper in 2017, and they show that this 2D magnetism, like you can see 2D magnetism even in the monolayer limit. And the reason behind this is that this magnetic anisotropy plays a key role, okay? And this stabilizes the long-range magnetic order down to monolayer and surpasses the effect of thermal fluctuations, okay? And this has created a lot of possibilities like CRI3, FGT. After that, a lot of new materials came, like CRI3, CGT, VAC2, and FEPS3. All are basically insulating or semiconducting, but the metallic like crystals are FGT-based system, which is our focus. In 1988, there was a paper where theoretically it has been studied the ferromagnetism in a ultra-thin films. Like there, they studied ferromagnetism in iron-based thin film, and they showed that this magnetocrystalline anisotropy plays a key role, and you can have a phase transition, ferromagnetic phase transition, if you have a small anisotropy like magnetocrystalline anisotropy, and you can get an analytical expression of the TC, which is J by this formula log of 3 pi J by 4 K. K is the measure of anisotropy, and using this you can see that this J is the exchange interaction coefficient, and if you have a strong, for example, in 3D case, this TC is solely determined by the J. So you have 1000 Kelvin or around TC for iron, for example. But if you are going to 2D limit, this K comes into the picture and your TC decreases. Okay. So the idea is that if you take how you can increase the TC in case of 2D van der Waals crystal. So one of the ideas is that you take a metal chalcogenides type of van der Waals structure and you incorporate this iron inside this structure, keeping the van der Waals system intact. Okay, and in that way you can get some kind of structure like FEX MCH2, where you can already see that iron is embedded in this system. And using this, there are of course several possibilities, but what people have found, only 3 structures they could actually stabilize, and these 3 structures have been observed in case of FGT kind of system, like Fe3GeT2, Fe4GeT2, and Fe5GeT2. The interesting aspect is that the TC has increased very much compared to the other van der Waals materials, like where other materials have a TC around 100 Kelvin or below. In this case, TC is, you can see already 210 Kelvin for first one F3GT, and then the second one discovered was F5GT 310 Kelvin, already room temperature, and what we are focusing here is Fe4GT2, where the TC is 270 Kelvin, near room temperature. Now, one more interesting thing is that in this paper, they looked at the anisotropy, and they saw that if you increase the anisotropy in this material, the TC increases. That is following a trend, except in this material where the anisotropy is low, but you have actually higher TC. So that is a puzzle in this kind of F4GT material. Okay. So with more background, like they showed that if you increase this iron in the unit cell, like that means you are increasing the iron-iron bond as a nearest neighbor iron-iron bond, then you can actually see that the TC almost linearly increases. For example, F3GT has a TC 210, where is a 3 iron in this case, and F5GT you have a maximum 310, where you have a 5 iron. So depending on the nearest neighbor iron-iron bond, you can actually increase the exchange interaction and you can enhance the TC, in spite of the fact that all 3 have different kind of crystal structure. Okay. And another interesting observation is that if you decrease the thickness, then below, for example, there are not many experiments, but there is one experiment where like they have shown that till 7 layer, you can see that the TC slightly increases. So there is if you decrease the thickness, you also change the anisotropy, and you can also increase the TC. That is the observation. Okay, particularly for F4GT system, the iron-rich van der Waals ferromagnets are promising spin source material. It can be promising spin source material because you have a high TC, high M saturation, and it's a metallic, so it's easier for spin injection. But only drawback is that it has less anisotropy. Okay, so this is the general introduction to this system. I'll give more introduction about the F5GT system. Let's see F3GT system, which is where you can see this is the magnetization curve, and you can see the magnetization increases, and this is some kind of non-monotonic behavior is observed, and it has a hexagonal structure, and it is a easy axis ferromagnet. That means the magnetization axis in the C direction. Okay, and people have observed the coexistence of antiferromagnetic and ferromagnetic order in this kind of system in this 150 to 214 Kelvin. Okay, and this is more extensively studied than the other two sister compound. Okay, and if you go to F5GT, you can already see the magnetism behaves very differently. Okay, so till now what has been understood that it's an easy plane ferromagnet, like the easy axis is in plane, and people have observed that complex ferromagnetic to ferrimagnetic kind of transition around at 275 Kelvin, and then they observed also glassy cluster state below 110 Kelvin. So these are the different observation in this material, and they also observed switch of magnetic anisotropy from in plane to out of plane in case of bilayer F5GT system. So it's a frozen spin glass like behavior in a monolayer F5GT system. These are I'm just telling, these are the experimental observation. There are not many studies. So people are still trying to understand the unusual magnetic behavior in this system. Okay, so with this basic introduction of the F5GT system, what I'll show you our interest in the F4GT system. So F4GT, you can see very nice van der Waals structure, and this is a high resolution image where you can see this structure as well from this paper. Now, if you see the magnetism, so magnetism you see around 270 Kelvin, the TC is there, and this is already an unusual behavior. You can see the magnetism initially increases and there is a spike and comes down. So this behavior was already studied by Professor Prabhat Mandal's group, and they said that it's a some kind of antiferromagnetic coexistence of some kind of antiferromagnetic ordering was also present in this case. So I'll not discuss this part, but the interesting thing is that if you see near 120 Kelvin, this magnetization curve was measured when the magnetic field is in parallel direction, and in this blue curve when the magnetic field is in Z direction. Okay, now you see after 120 Kelvin it switches. That means there is a change of spin orientation, easy axis orientation if you go below 120 Kelvin. And in literature, this has been described as a spin reorientation transition, and in this high temperature limit, the easy axis is in plane, and if you go to this direction, below this 120 Kelvin, the easy axis changes to C direction. Okay. Now you can see this also in the image curve. Image curve, you see that image curve also flips. So that means there is a competition between shape and magnetocrystalline anisotropy as a function of temperature. That's what probably happening.
Sorry, I have a question.
Yeah.
This anisotropy, does it depend on the thickness?
Yes, it should depend on the thickness. What people have, I showed in the previous curve, like what people have observed.
This temperature, will it depend on the thickness?
It should depend. People have observed the spin reorientation temperature. Nobody has measured the anisotropy before, but what people have observed that till 7 layer, below 7 layer, it has a dependence. Spin reorientation has a dependence on thickness. But above 10 nanometer, it's fine. It has a weak dependence. Okay? Yeah. Gap opening means. Oh, there is a history. This is bulk material, so hysteresis is minimal. So you probably zoom in and then probably you can get. Yeah. I'll show you hysteresis in our sample. Okay. Now, we also did some experiment with min2 monodal sample from IISc, and they measured actually specific heat, and they observed that actually there is a kink in this specific heat, and this suggests this is a thermodynamical transition, okay, some kind of anomaly in the specific heat. So what we wanted to do the transport measurement, because these are metallic sample, and there are very few metallic ferromagnetic 2D samples available, and we wanted to look at the transport behavior. Okay, so but doing transport is not easy in this material, because these ferromagnetic 2D materials often can oxidize, and what we have to do make a good contact. So the strategy what we have taken, we have the transfer setup, and using the transfer setup, first we make the electrical contacts, and these can oxidize, but what we did, we made the device, and within half an hour we using PTMS, we put the flake on top of this contact, and immediately we coat PMMA. So that's how then we check the electrical transport, and we found that it can give a very nice contact, and the temperature dependence RT data, what you can see, actually we made two devices, we did extensive transport on two devices. One is the thick layer limit, like 95 nanometer, and one is the thin layer limit, which is 16 nanometer, okay? And both of them showed almost identical, like similar type of transport features. So in this case, you can see interestingly that if you see the rho versus T curve, this black line, you can see that initially resistance, it shows metallic-like behavior, but near the phase, like ferromagnetic transition, which is somewhere here, 270 Kelvin, there is almost no feature. Okay, there is a very weak signal. But if you come closer to spin reorientation transition, which is around 100 Kelvin, 120 Kelvin, you can see there is a dramatic fall of this, like resistivity curve. That means it becomes more metallic. Okay, so then you can see also in the derivative, you can see two peaks. Basically, one is around 116 Kelvin, and another small hump we observe near 38 Kelvin. I'll come to this point later, because we see basically two humps. I'll show you the consequence of this on the transport measurement. So then we try to analyze the transport resistivity data. If you see the literature, you can model this resistivity in this ferromagnetic metal. You have all different type of components. One is the residual component. Then you can have the electron-electron interaction term, which should go as T square. And then you can also have electron-phonon term, which is typically proportional to temperature. And you can also have an electron-magnon term. And electron-magnon scattering is proportional to T square. So then we try to fit the data. So you can see, if you feed the resistivity data as a function of T square, it shows very nice behavior till like Fermi liquid type of behavior, like till 40 Kelvin. But, and you can also fit the whole data, like first part is T square, then second part you have both T plus T square type of term, and the high temperature part is dominated by mainly electron-phonon term. Then what we did, we actually can fit the data in both the devices, and you can see the hump is present in both cases, and you can get almost the similar characteristics. Okay. Now to understand the low temperature part, whether like you have electron-electron interaction can give you T square, also electron-magnon can give you T square. So to understand which is dominant in which case, we did the magnetic field dependence. And if you do the magnetic field dependence, what you observe that at low temperature part till 40 Kelvin, you see almost no magnetic field dependence of this resistivity curve, very weak dependence. But if you go to this, above this hump, you can see that there is a huge magnetic field dependence. So from this, we can actually conclude that this part is dominated by mainly electron-electron interaction, and it does not change with the magnetic field and behaves like ordinary metal what we see, right? But above this term, you have a strong electron-magnon interaction, which is changed by which is modulated by the magnetic field. So we can say that this T square here in this regime, electron magnon is significant. Then what we did, we studied the Hall effect, usual Hall effect, and this is the magnetization versus magnetic field curve, and this is our rho xy versus magnetization curve. So thanks to the previous speaker, he already mentioned that this magnetization, this Hall data should have two components. One component is of course the ordinary Hall data, and another will be the anomalous Hall data, right? Anomalous Hall coefficient, RS. So we show, let's see the two results. Before that, actually, I'll show you the magnetoresistance data. So magnetoresistance data, you also observe very interesting observation. Like if you plot the magnetoresistance from the two devices, in these two devices you see the magnetoresistance is predominantly negative in this system, except above this 40 Kelvin, like below this 40 Kelvin. Below 40 Kelvin, magnetoresistance becomes positive. But above this 40 Kelvin, you see magnetoresistance is maximum near the spin reorientation transition. So negative magnetoresistance is very common to this kind of ferromagnetic system, because if you apply magnetic field, you suppress the spin flip scattering and you get a negative magnetoresistance. Okay, but this positive magnetoresistance is very uncommon, because you basically get the orbital contribution. In this case, there is no magnon, almost negligible magnon contribution what you observe in this region. Okay, so I'll show you the experimental result what we observed first, and then we'll discuss the. So we also observe, if you measure the like MR, anisotropic MR, angle dependent MR, you can see very nicely near the spin reorientation transition, this phase shift is, you can get like a cos-like curve to sine-like curve, something like that. So this one, yes. Okay. So also Dhawala was asking about the hysteresis. You can see in the 95 nanometer thick layer, we also observe this hysteresis, and if you go to the thinner layer, it becomes more hard magnet type hysteresis. Okay, so now I'll come to the very interesting result of the Hall data. If you plot the Hall data, what you observe that Hall data, like from two devices we have plotted, and we can see that this Hall data shows a very interesting transition. Initially it was positive, but near the spin reorientation it changes sign. But if you observe again, around 40 Kelvin, it again changes sign. So that means there is a Fermi surface reconstruction is happening near spin reorientation transition as well as at a lower temperature. So that means there are two kind of transition is happening in this material. Okay. So we also observe the anomalous Hall effect, and we get significant anomalous Hall effect data, and I'll not discuss this anomalous Hall effect in detail, but what we try to observe, the magnitude is high, and yes.
That is the high field rod.
This is high field, yeah.
This is more like a carrier.
Yeah, more like a carrier. Yeah, that's what. If you assume the single band model, of course. Then we observe the anomalous Hall data, and anomalous Hall effect also shows some kind of scaling behavior, where is alpha is not 2, it is 1.7 and 1.68 in these two devices. So you have it, you don't have only intrinsic mechanism, you have also extrinsic mechanism present, and there are some theoretical calculation. One is by our in-house professor like Ramanujan Kumar's group. They already observed that in case of DFT, they did the DFT calculation, and they showed that F4GT is some kind of shows some kind of different magnetic class. Okay, they observe intrinsic Betti curvature in this material, and this suggests that anomalous Hall effect can come from this intrinsic origin. Also, there are some theory calculation by Biplav Sannal's group in the same line. They observed the this theoretical calculation suggests the similar kind of results. Now, Mintu Mondal's group did the experiment in case of bulk sample, and they observed this scaling coefficient is close to 2. So they predict that they say that it's mostly from the intrinsic origin. But what we feel that we have a strong electron magnon interaction in this region. So and also this anomalous Hall effect has a dependence on the side jump origin, side jump mechanism, then this will not be solely from the intrinsic origin. So this temperature dependence of the anomalous Hall conductivity comes also from the extrinsic origin. So I'll not go into the detail. We have done the detailed analysis of this data, and we actually gave the different component from intrinsic and extrinsic origin in our work. So then we talked to the Tanmay for understanding these Hall data. So Hall, you have a near the spin orientation, you have a sign change, right? There is a Fermi surface reconstruction. So it's already difficult to do DFT calculation in this kind of ferromagnetic metal. But what they predicted that there are two very energetically close phases available. One is the collinear and another is the non-collinear phase, and the energy difference is only 10 millielectron volt, which is close to 100 Kelvin, 120 Kelvin or so. So they say that these are the two phases possible scenario. These are not the only possibility, but these are the two possibilities. And if they calculate the electronic structure, they see that in these two cases, there are appearance of new Fermi pockets, okay, in these kind of non-collinear phase. And that can explain our Hall data. But that cannot explain the low temperature phase transition what we are observing. So there are a lot of unclear thing in this kind of material itself, okay. So in the last 10 minutes or so, what I will discuss the electron spin resonance experiment, because transport data, what we observe that we have a Fermi surface reconstruction, we have two kind of transition in the Hall data you observe. We also observe in the resistivity data as well as in the magnetoresistance data, okay. Now to understand or measure quantitatively the anisotropy, the ESR experiment can give you a lot of details, okay. So we under this MOU, my student Riju went to Dresden for 6 months, and he did this experiment, ESR experiment with Alexei Alfonsov and Vladislav Kataev, okay. So ESR, a brief description to introduction to ESR. So I think most of you have done the ESR experiments in the masters, where for a paramagnetic sample, what you do, you apply a magnetic field and you create a Zeeman gap, and as if you sweep the magnetic field, keeping the microwave frequency constant, you will see a resonance, okay. Now this ESR technique can, using ESR technique, you can of course determine the G factor, you can characterize the magnetization anisotropy, easy axis, Magnon exciton gap, all these things you can determine. Also you can determine the spin-spin correlation, okay, and spin dynamics above TC, if you have a short range correlation in this system present or not. So this Dresden lab, they have a frequency range 10 gigahertz to 950 gigahertz, and magnetic field they can go up to 16 Tesla, and temperature range 2 Kelvin to 300 Kelvin. And this is the experimental setup of the lab. And if you do this, if you apply this magnetic field in case of ordered state, what will happen? In case of ordered state, if you apply magnetic field, then it will start precessing following the Landau-Lipschitz equation, okay. And for an isotropic ferromagnet, if you don't have any kind of anisotropy, then if you apply magnetic field, it is the H external is nothing but the this effective magnetic field, and the resonance condition will be something like that, Larmor frequency equal to gamma into H external. Now if you have some kind of intrinsic anisotropy in your system, what will happen? This H effective will be equal to external magnetic field plus the anisotropy field, right? So the resonance line will shift. Depending on the shift of the line, you can actually measure accurately the anisotropy in the magnetocrystalline anisotropy in the system, okay. So if you just solve this equation, you can solve this equation for easy axis ferromagnet, if you assume the axis in the C direction, for example, or you can assume the easy plane ferromagnet, you can get this kind of solution like H nu equal to G mu B mu naught H plus mod HA, and vice versa, okay. So we'll so the thing is that we get the data and we try to fit the data using this model. So what we get? So very interestingly, this is a ESS spectra, temperature dependent ESS spectra of FGT at a fixed frequency. Okay, what you see that this line, this solid line is actually the paramagnetic line. Okay, if you don't have any anisotropy, it should follow this line. Now you can already see at low temperature there is a huge shift from this line, and at high temperature the shift is in the opposite direction, right? So that means already the anisotropy is changing sign from high to low temperature, that you can see, and this shift is happening near 120 Kelvin. So then if you plot the other frequency, it shows overall the similar kind of behavior. Okay, now let's go to the if you apply the previous one, the magnetic field was applied out of plane. Like if you see this sample, you apply the magnetic field out of plane, that means in the C direction. Now if you do the same measurement keeping the sample in plane, like magnetic field you apply in plane, then you get the spectra where the shift is in the opposite direction. Okay, and you can see the exactly similar kind of data what you observe. Now as a function of frequency, you see the similar kind of effect. So it's almost frequency independent effect. Now you can plot this anisotropic field as a function of temperature. This field, this point, peak point, by fitting this data, you can plot, and you can see that you can see as a function of temperature, this field actually changes sign near this TSR, what is around 100 Kelvin. And here also this is H parallel to AB, this is a different frequency, and 3 different frequency, it shows almost the similar behavior, right? So then first thing what you can do, you can determine the G factor by doing the frequency dependence, and G factor remains almost constant in this case, and it's almost close to 2.1. However, at low temperature there is a slight deviation, 2.06, and you can also see there is a deviation if you plot this frequency dependence data for this H parallel to C and H parallel to AB, there is a deviation. So I'll discuss the deviation later, but more or less the G factor is 2.1 in this range, 2.1 plus minus 0.01. Okay, so using this G factor, what you do, you put, okay, before this we also check the if you have in plane anisotropy. So for example, you put the magnetic field in keeping this sample in this orientation, and you change the orientation in plane, and you see there is no in plane anisotropy in this case. Okay, so F4GT does not have an in plane anisotropy, but it has a out of plane anisotropy. So now I'll put the summary of the data, ESR data in this case. Okay, what you observe, so this is the H parallel to C, red data is H parallel to AB, and this blue data points are the H parallel to C, and you can see there is a deviation. This is more or less agreeing, but at low temperature it actually deviates below, and this temperature is close to 50 Kelvin. Okay, now one can actually assume that total anisotropy field, you have 2 components, right? You have basically, one is the magnetocrystalline anisotropy, which is intrinsic to the structure of this system, like it comes from the crystal structure, spin orbit coupling, dipole-dipole interaction, etc. And the second thing is the shape anisotropy. Shape anisotropy, because you are in the 2D limit, you obviously have the shape anisotropy. Now shape anisotropy one can calculate from the magnetization, MS versus T plot. One can of course you have to assume the 2D limit, and shape anisotropy should go like this. It should not have any kind of non-monotonic behavior. Okay, I'm not talking about the values, but you can see that this should go as a function of temperature, it should behave like this. Now why do you have a change in anisotropy? Like if of course if you subtract this total from this shape anisotropy value from this total value, you can see that this magnetocrystalline anisotropy overall negative, but it has a dramatic change near the spin reorientation transition. Okay, it actually increases very much after the spin reorientation transition. And more importantly, near this 50 Kelvin, I told you these models. What has been used to fit this data is the uniaxial ferromagnet. Okay, using this model, you can feed the data and you can see there is a deviation, and that means the present theory cannot explain this data. So this deviation cannot be explained below 50 Kelvin. So overall, now if we couple all the transport data and the ESR data, we can see that this, of course, ESR data shows very rich anisotropy behavior, and it matches with the transport data as well. I told you that near the spin reorientation you have a transition, and there is a change of anisotropy, and low temperature also you have a deviation. So that also you observe in the Hall data, magnetoresistance data, everything. So everything matches well, but we don't understand exactly why it is happening. Okay. So to understand a bit more, we did the like temperature dependent XRD measurement, whether if there is any structural phase transition or not. So if one, like this was also done in IISc Dresden, and they did a single crystal XRD measurement, and they observed as a function of temperature, it decreases, it behaves normally, like it doesn't have a dramatic phase transition, structural phase transition. So you can see the data, it's C by A ratio all within the error bar. So from this data you cannot conclude if there is a structural transition. So to do more, what we are performing right now, the Raman spectroscopy. And Raman spectroscopy, this is also this is a new data, and what we are observing there also we see very interesting observation near the ferromagnetic transition. We have the data now till 350 Kelvin. Near the ferromagnetic transition, we don't see much of a change. That means near ferromagnetic transition, lattice and the magnetism are not that much coupled. What do you observe from our data? You can actually fit an harmonic model to that. But near the spin reorientation transition till 77 Kelvin we could do, and you can see there is a clear drop of this signal. It doesn't follow the anharmonic model, just pure temperature dependent model. So that means the spin phonon coupling definitely is changing here, and that is probably there is a lattice and magnetism is mixed in this near this 120 Kelvin spin reorientation transition. So with this, I think I'm on time, so I'll just summarize my talk. So first thing what you observe, that resistivity, we did a detailed understanding about the scattering process, what is happening, and we observe like ordinary Hall, unusual ordinary Hall effect, where we see Fermi surface reconstruction. There are two transitions from the Hall we can determine. Then we see also in magnetoresistance, we also see two transitions, like one here and one here, that is in line with your previous this observation. And also we say that anomalous Hall effect, both intrinsic and extrinsic origin, which are dominant in this material. And then ESR measurement says that there is a change of competing anisotropy, and the spin reorientation is nothing but a competition between shape anisotropy and the magnetocrystalline anisotropy. And then the DFT calculation at least show that two phases are there which are possible in this material, which may be the spin reorientation driven phase. One is spin reorientation driven phase, and another is collinear phase. And with this actually, these are the main observation: unusual transport features due to spin orientation and low temperature phases below 40 Kelvin what you observe. And with this, I want to thank you all, and these are published in these two materials, these two journals, and we have lot of questions after this experiment. Thank you.
Question.
If you go back, there was this anomalous Hall data,
I
where
have to go
the
back
hysteresis is not conventional.
Sorry?
The hysteresis is not a conventional anomalous Hall, but there is much more to it. Do they correspond to some spin textures?
You mean hysteresis?
No, can you just go back?
Here.
Yeah. If you look at something like 120 Kelvin and below,
Yeah,
that is much more than
that is what we do. Everything magnetoresistance also increases very much near the spin reorientation, and also hysteresis is maximum there. So we actually don't understand much about this data. Okay, that's fine.
So the additional bumps, there is, I mean, below 120 Kelvin. we
Yeah,
don't
this
know.
also we don't understand much. We see this kind of effect, but we have not understood in detail.
Is there possibility of some strain dependence below certain?
Of course, there could be because you see the spin reorientation. There could be collinear phase, and there could be magnons which are coupled with the phonons, magnon-phonon coupling. This can also give rise to new phases, and this 50 Kelvin phase we don't know. So this is some kind of unusual phase, and this can give rise to really funny things. Yeah.
No, but to know that, you have to see the magnetization data also carefully.
Magnetization, we checked it. There is no features.
No, also there is no hysteresis.
Magnetization, this was done in a bulk sample, and the magnetization, of course, you have to do in a single crystal, and there the hysteresis is not that prominent. Yeah, this is only in the thin layer limit what you get. Yeah. No, actually, that's the question referee asked. Why compared this? First of all, in 2D limit, that's why you are seeing the hysteresis. This is already there in bulk, and hysteresis is more prominent in the 2D case. You are going to the hard ferromagnetic regime. This is one example, and another thing is in the Raman spectroscopy, we see different signature in the thin layer compared to the 2D layer. So it's not pure bulk. We want to go down, but it's not easy like graphene. And problem is that, of course, we are trying to make devices, and if we need to do in a globe box, which we are still developing. But what we are seeing that immediately after this, if it is bluish color of flake, it's not easy to exfoliate going down to a monolayer limit. People have tried some kind of alumina oxide based technique, or that we have not tried, or gold deposited like exfoliation, that we have not tried yet. But the main problem is that you have to perform everything inside globe box, otherwise in the thin limit you cannot do. We did make devices, but it did not work.
Yeah. I think I have a comment or suggestion, whatever it is. So you are cleaving the sample in the air, okay, and after within half an hour you are trying to encapsulate with that. So of course within that time some of the surface layer will go something else.
Yes.
Exactly. So I can think of a scenario where the layers near the
it can be. You are right, but the thing is that the transport data where these humps, we are not considering that much. We are not saying that much. These cases we are not considering at all. That's what the details we are not focusing on. But the main result, that resistivity data, where you see actually very nice contact. First of all, now when we are making the thin flakes, what we are observing, we are getting contact resistance is observed a mega ohm or so, because we had thin flakes are very prone to oxidize. But when you're in the bulk limit, the oxidation rate seems to be lower. I agree, but whatever be the whatever be the effect, we are not being. One needs to characterize. We could not see. There is no report till now. We are trying to understand the surface effect. Yes.
Any further question? If not, then thanks the speaker once again for fantastic talk.